Welcome back to the second half of the basic MIDI lesson. Previously, we covered many basics of the MIDI protocol, how we capture serial data from the UART serial port, did a quick study on how hexadecimal values work, and we got to see how the code parsed the data from the UART into proper MIDI messages. Now we are ready to go process a MIDI message using the process MIDI function. We see at the beginning of process MIDI, MIDI command equals MIDI RX0, MIDI note equals MIDI RX1, and MIDI velocity equals MIDI RX2. Copying all this over may seem redundant now, but can be useful later on. For now, we can see more clearly what each byte is for. Our first if statement is right here. We check to see if MIDI velocity is nil or 0. And we also check to see if MIDI command equals hex 90. If both match the criteria, we move on with the rest of the code, which will be to call the MIDI note off function, then reset the UART receive interrupt, and finally return to the previous function to cease checking any more if statements in the process MIDI function. The command hex 90 is a MIDI note on command. As stated in the previous video, some keyboards may actually transmit a note off as a note on command with velocity value of 0. Think of it as a note on with 0 volume. We will get to the MIDI note off function after we look at the rest of the if statements inside process MIDI. The next if statement is right here. The command hex 80 is an actual note off command. So again, we will call the MIDI note off function if the command byte equals hex 80. The last if statement we're going to take a look at is right here. Again, we are looking at the hex 90 command. Since we managed to get past the first two if statements, then we must have a true value in MIDI velocity. So we will now interpret hex 90 as a note on command, and we will call the MIDI note on function. Now I should mention that the code is hard set to accept note ons and offs from MIDI channel 1. We could add a few more steps to let us select which channel, but to keep things simple, we will stick to channel 1 for now. The channel value is right after the command byte's most significant nibble. The least significant nibble is the channel value. So if our command byte were hex 83, 8 is the most significant nibble and 3 is the least significant nibble. In this example, we would be saying note off channel 4. Channel 1 is hex 0. Channel 2 would be hex 1. Channel 3 would be a hex 2, and so on up to channel 16 is hex F. Just remember, the hex value is actually one value lower than the channel number. Now there is a couple extra if statements here that we are not going to go over in this lesson, but we will continue with them in the next few lessons. But for right now, we're just going to concentrate on MIDI note on and MIDI note off. So we will continue with those functions further down here with MIDI note on. Taking a look at the MIDI note on function, we have an if statement, and then we have that followed by some other code. We have a few variables I'd like to go ahead and explain. Voice array is an array that we keep note number values stored in. Note is the note number that we passed on to the function from a previous function. Current note will be the current note playing. Note count is used to keep track of how many notes we have playing at any time. In the first half of our MIDI note on, we have an if statement checked to see if note count equals 0, a false value. If it is false, Then we first save the MIDI note value to the 0 position in the voice array. Next, we turn the volume on so we can hear the note play. Then we copy the value of voice 0 to current note. Before we exit, we +1 to note count. And in this instance, note count should equal 1. And finally, we return to the previous function, which will take us back to the super loop. Now, if note count was actually greater than 0, which would be true, the first if statement would be ignored. op1.amp equals 0, which will silence the current playing note for a very, very brief moment. Next, we need to scan the voice array for the first empty spot we can save our new note to by using these for loop and if statements. For integer I equals 0, as long as I is less than 16, I++, and if voice I equals 0. What this does is it keeps adding +1 to I like a regular for loop, but we also use I to peek into the elements of the voice array. The first element we find equals 0 will allow us to run the rest of these operations. Voice I equals note. So it will store the note that was passed on to this function into voice I. And that could be voice 0, voice 1, voice 2, voice 3, on up to voice 16. The next operation is current note equals voice I. In other words, the value of note is saved to current note. The next operation is we turn the volume back on, followed by adding +1 to the note count, and finally we break out of this for loop so that it doesn't continue running. After that, we will be at the end of our function and it will return to the super loop. So for example, if we had 3 notes saved already, that would mean voice 0, voice 1, and voice 2 would all have a value in them. Once we got to voice 3, it would equal 0. Then we would have to save the note value to voice 3. Then the current note would equal that note value. Then we would turn on the volume, increase the note count, and break from the for loop. The point of all the above code is to emulate how a monosynth plays. When we press down one note, it plays. If we hold that note down and press another, the first note will stop playing and the new note will begin to play. And as you will see when we continue, if we let go of that second note while still holding down the first note, the second note will stop and the first note will start playing again. So you can do some fancy trill note playing like this. Now let's look at the function for when we release a key. It has many similarities to the note on code. We begin with an if statement. If note equals current note and note count is greater than 1. What this means is if we release the note we are hearing while we are holding down other notes, we will run the rest of this code inside of that if statement. This will turn the volume off, and this will scan for the note that we just released. We begin with a for loop. We check to see if the current element we are scanning equals the note value we just passed. So if voice 2 equals note, then current note equals voice I minus 1, which would be the previous note saved in the voice array. We would turn the volume back on. Voice I, which would have been voice 2, will equal 0, and we will reduce the note count by 1. Finally, we will break the for loop, and once we get out of the for loop, we return to our super loop, which eliminates running the next if statement. So what's going on here is notes are saved in the order they were pressed. So the last note in the voice would be the current note, and the note played previously to that one is in a location where it was -1. This is again where we are emulating a monosynth. We want to restart a previously held note when we release a note, and we want to keep them in order, track them, and remove them as needed. Now, if the first if statement was not met, we'd end up in this next if statement. If note count is less than 2, op amp equals 0, voice 0 equals 0, note count equals note count minus 1. If note count is less than 0, then note count equals 0. If we ended up running this section, we only had one note held down. Once it is released, no other notes will be playing. And here we have the final if statement. If note count is greater than 1, we can run a for loop to find the note in the array. Again, we check to see if voice I equals the note that we just released. We assign voice I equals 0. Then we start another for loop that has an integer c equals I plus 1, as long as c is less than 16, c++. Then inside the loop we do voice I equals voice C. And what this is doing is it's shifting all notes past the removed note to the left by 1. We end with voice 15 equals 0, note count equals note count minus 1, and then we break from the for loop. So basically we end up here if a current note is still playing, but we released one that is not playing. The silent note release will be removed from voice array, and any notes past its position in the array will be shifted to the left to fill in the void it left behind. Now let's take a look at what we do with current note so our op1 oscillator plays the correct frequency. When we press a key on our MIDI keyboard, we are sending a MIDI message to our BP synth. A message like this, 903C7F, is translated as note on, middle C, velocity 127. For now and in the next few lessons, we are not going to process velocity. Instead, we will default any note on with a velocity greater than 0 to maximum volume. This is why we are directly writing 1 or 0 to op1 amp. When we write 1, it is the maximum volume. 0 is off. Later on, we will replace op1 amp equals 1 with a call to trigger the envelope generator. For now, we will focus on the MIDI note number. In the example, it is MIDI note number 60, which is hex 3C. When we look at a MIDI to frequency conversion table such as this one, we can see the MIDI note number 60 and its frequency. Taking a look in wavegen.c and make sound, we find this operation. F0 equals 440 times 2 to the power of current note minus 69 times 0.08333333. Here we can see where we use current note for our MIDI note on. We use this formula to derive a frequency from a MIDI note number. Please take note that MIDI note number 69 is 440 Hz in the MIDI note to frequency table. The formula is using frequency 440 as a midpoint reference for the range of notes we intend to use. 440 Hz is tied to MIDI note number 69. We want to know how many notes the current note is from note number 69. So we subtract 69 from the current note value. If current note is less than 69, we end up with a negative value. If current note is greater than 69, we will have a positive value. Since there are 12 notes per octave, we use 0.08333333 to divide our current note minus 69 result by 12, and we do that by multiplying the value of 1/12, which is 0.08333333. Using an exponent with a base of 2, we apply our result from current note minus 69 times 0.08333333 as the power. When we use an exponent with a base of 2, we get some interesting results. 2 to the power of 1 equals 2. 2 to the power of 0 equals 1. 2 to the power of negative 1 equals 0.5. We can use these behaviors to our advantage, and you will see it used several more times in later lessons. Let's do some quick examples. If current note equals 69, we would have 440 times 2 to the power of 69 minus 69 times 0.08333333. This equates to 440 times 2 to the power of 0 times 0.08333333, which equates to 440 times 2 to the power of 0, and finally we have 2 to the power of 0 equals 1, and 440 times 1 equals 440. The chart indicates note 69 is 440 Hertz. If current note equals 57, which is 12 less than 69, we'd have negative 12 times 0.08333333 equals negative 0.9999996. 2 to the power of negative 0.9999996 equals 0.5 when you round it down. And I'll be rounding numbers sometimes in these lessons just so we can avoid ridiculously long numbers like the one we just saw. 440 times 0.5 equals 220 Hertz, 1 octave below 440 Hertz. And the chart confirms this when we see note 57 equals 220 Hertz. If current note equals 81, which is 12 more than 69, we'd have 12 times 0.08333333 equals 0.9999996. 2 to the power of 0.9999996 equals 2, rounded up. Thus, 440 times 2 equals 880 Hertz, which is 1 octave above 440 Hertz. Again, the chart confirms this value when we check that note 81 equals 880 Hertz. So if we play a note 1 octave above note 69, we double the frequency. If we play a note 1 octave below 69, we divide the frequency by 2. Any notes in between each octave will be 1/12 more or less, depending on how much more current note is above or below our base note of 69, and which octave we are in. Note 70 would be 1/12 of an octave above 69. 71 would be 2/12. 72 would be 3/12. And on up to 81, which would be 12/12 or 1 full octave. Same works in reverse. 68 would be negative 1/12. 67 negative 2/12. 66 negative 3/12. Down to 57, which would be negative 12/12 or negative 1. If we continue going up or down, we'd end up with fractions such as 13/12, 14/12, and when we arrived at 24/12, it would equal 2, which would be either a +2 or -2, depending on which direction you were going. And this would be taking us up 2 octaves or down 2 octaves. Let's give this a try using MIDI note number 53. F0 equals 440 times 2 to the power of 53 minus 69 times 0.08333333, which equals 440 times 2 to the power of negative 16 times 0.08333333, which further equates down to 440 times 2 to the power of negative 1.33333328. 2 to the power of negative 1.33333328 equals 0.3968502776663. So you take that number times 440 and you end up with F0 equals 174.614122176161. Taking a look at our MIDI note to frequency table, we can see that MIDI note number 53 is nearly the same as what our formula returned us. It can be off by a tiny bit like this. No one's going to notice the difference. We really don't need to analyze this formula any further. The formula will work for us every time for every MIDI note, but we will revisit this formula again in the next lesson when we modify it for our own purposes. Once we have our frequency calculated and assigned it to F0, we now have a value for wave compute to use when it goes to create a sample for us. In this lesson, we've covered a lot with the MIDI interface, message parsing, and note to frequency conversion. Be sure to completely understand these as they are crucial for controlling our synthesizer. In the next lesson, we are going to see how we get the pitch bender working.